Alright, in this lesson, we're going to talk about the second kind of reactions, which are called decomposition reactions. These are either going to be A, the hardest kind, or B, the second hardest kind. Decomposition or single displacement, which we'll do next, are some of the flip-flop between students between which are the two hardest ones. Personally, I feel like single displacement might be a little bit harder, but again, some students think that decompositions are a little bit harder. So everyone's different, but let's get to this. For decomposition, decomposition is the complete opposite of synthesis, the complete opposite. In this one, we have a single compound, just a single reactant that breaks apart into two or more simpler substances. So again, unlike synthesis, which creates one product, in decomposition, we only have one reactant, and it breaks into more than one product. So the general equation for this is AX, and it splits into A plus X. A is any element, it's a cation, X is the anion, but it doesn't always look just like that. This is showing you that, oh, it's just two elements that split apart, and that really does not happen, except for the first example we're going to look at. It's actually way more complicated than this. But again, in the last video I said that chemical reactions are like relationships. So synthesis is you have two single people and they come together and go out. Now that couple are tired of each other, they've been together for a while, and they're like, you know what, we just need to break up. And that is decomposition. It's breaking up. You were a couple, now you're single again. It's like a divorce. Now, there are 4 or 5 different kinds of decomposition reactions. So let's look at the first one. This is the easiest kind. It says the decomposition of binary compounds. All you are doing for this one is you're just literally splitting the thing in half, whatever the compound is. You just split it in half into its two components. So you take the metal, you take the non-metal, and you just break them apart. Just like what the general equation AX yields A plus X looks like. You just literally split this in half. So an example would be, I have HgO, or 2HgO, yields O2 plus 2Hg. Mercury 2 oxide yields oxygen plus mercury. So literally all I did was I took the, whoa, this is not calibrated whatsoever. Let's just ignore writing stuff. Again, all I did was I just took the mercury, I broke it apart off the oxygen, and that was it. I literally just split them in half. Actually, I need to calibrate this, so let's do that together. Okay, now we can go back to this one. So, now that I calibrated the smart board, let's try that again. There we go. I just took the Hg and I just split it off. Okay, so the Hg comes off, and then I just take the oxygen and I break the oxygen off. So that's decomposition. I just split it in half. Another example could have been something like sodium chloride. Now, that coefficient 2, I know it's going to be there, so that's why I'm doing a shortcut. But sodium chloride, I literally just split it into its components. So it's sodium plus chlorine. I just split it in half. Again, that's the easiest kind. And here's where we're going to start to get a little bit more complicated. Decomposition of metal carbonates. So in this one, I'm going to give you some kind of metal and a carbonate, like calcium carbonate, iron 2 carbonate, sodium carbonate, some kind of metal, then a carbonate. When you do this, when you decompose a metal carbonate, you will always make a solid metal oxide and carbon dioxide gas. So again, the equation for this is MCO3 yields MO plus CO2. That M is whatever the metal is. Now granted, I didn't balance charges on this because I don't know what the metal is. But notice I always make a metal, whatever the metal is, oxide plus carbon dioxide. Always CO2. Every single time. Could you put the CO2 first? Could you say CO2 plus MO? Absolutely. That order does not matter. I always put CO2 at the end just because that's what I'm used to. So let's look at an example. Again, I have calcium carbonate, and so my metal in this case, my metal is calcium. And so I make a metal oxide, so my metal is calcium. So I put calcium oxide plus carbon dioxide. If for some reason I had sodium carbonate, it would be sodium oxide plus carbon dioxide. And that is actually already balanced, so that works out. So again, you take whatever the metal is, and you make that metal oxide plus carbon dioxide. Again, there's no easy way to do this other than to memorize this. Memorize your equations. You have to memorize. When you see a carbonate and you see it's decomposing, your brain instantly needs to say, okay, I am going to take the metal, I'm going to add it to oxygen to make it a metal oxide plus carbon dioxide. So anytime you see a carbonate decompose, you know, oh, it's a metal oxide plus carbon dioxide. Just has to happen that way. No ifs, ands, or buts about it. All right, next one. Ooh, metal hydroxides. This is actually very similar to the synthesis one, it's just backwards. So in this case, you're going to start with the metal hydroxide, and you're going to produce the metal oxide in water this time. So this time, as you see, it's the metal hydroxide, and you make the metal oxide plus water. This is the complete opposite of what we did in synthesis. In synthesis, we started with the metal oxide and water, and we made the metal hydroxide. Now we're going backwards. So again, the metal is the only thing that ever changes. All you really need to do is substitute out the word metal with whatever metal I give you. And that's it. You just substitute out the word metal for whatever I give you. So in this example, I gave you magnesium. So magnesium hydroxide makes magnesium oxide plus water. I'm on a sodium kick, so I'll just use sodium. Sodium, well, I'll use the symbols. Sodium hydroxide makes whatever the metal is, in this case sodium, sodium oxide plus water. And then, again, because it's NaOH, there's only one Na, there's two Nas, I need two right there. And there you go. That gives me two O's, two oxygens, two hydrogens, it's balanced. Some go, okay, what about that solid business? Do I need to put solid down here like this and gas like this? No, you don't really need to do that. If you ever take chemistry in college, you might have to do that. Some professors make you, some don't, but just so you know, that's kind of what it makes. It makes a solid, and it also makes a gas. That's not super important. I'm not going to hold that one against you. So you do not need to put the S and the G or anything like that. Couple more. Ooh, chlorates. All right. This is one of my favorites. In fact, we're going to do this in a lab very soon. When you decompose a metal chlorate, you always make the metal chloride an oxygen gas. So again, it's MClO3, because ClO3 is chlorate. The M is any metal I give you. It yields MCl, which is the metal chloride. Again, the metal is whatever metal I give you, plus oxygen, which is diatomic, hence O2. This is actually one of the ones we're going to do in the lab. We are going to decompose potassium chlorate, and it makes potassium chloride plus oxygen. One thing that's really important actually is that whenever you do these in a lab, sometimes you have to use a Bunsen burner. And so whenever you use a Bunsen burner, you have to show that in the equation. How? Well, we put a little triangle underneath the arrow. That triangle means heat. That triangle means heat. So whenever you add heat, whenever you burn chemicals over a Bunsen burner or any kind of heat, even a hot plate, you don't have to be a Bunsen burner, it could be anything. Whenever you add heat, you have to put a triangle underneath the arrow. This example is actually also going to use what's called a catalyst. Catalyst. A catalyst is something that speeds up reactions. It makes chemical reactions happen much faster. So again, a catalyst is something that speeds up chemical reactions. And where do we write the catalyst? It actually goes on top of the arrow, because a catalyst, even though it's used in the reaction, well, actually I shouldn't say that. It's used in the experiment, but it doesn't actually mix with the chemicals. All it does is it helps chemicals react quicker with whatever they need to do. But the catalyst itself does not react with any of the chemicals. So a very common one we use is manganese dioxide, MnO2. And the catalyst always goes above the arrow. So notice, again, the catalyst goes above the arrow. Again, notice there is no Mn anywhere in the product side, because again, the catalyst is not used in the reaction. It doesn't mix with the chemicals. All it does is it just speeds up the reaction. It makes it happen much faster, kind of like the heat. And so when you add a catalyst and heat, then it really makes it go faster. Is this super important? Yes and no. Is it important when we do these in class? No. Is it important when we do them in the lab for lab reports? Absolutely. So when we do a lab report on this stuff, you better make sure anytime we add heat, you put a triangle under the arrow. Anytime we use a catalyst, you write the catalyst above the arrow. That is very important anytime we do a lab report. All right, let's pick a different metal this time. Let's pick, how about magnesium? So I have magnesium chlorate. And again, I want you to ask yourself, what are you going to make? What is the metal? Good, it's magnesium. And so it's the metal chloride, so magnesium chloride. I just balance the charges, that's why it's MgCl2, balance the charges, plus oxygen. Since oxygen's by itself, it's diatomic O2. Now I just need to balance this. One magnesium on reactant side, product side. Two chlorines, that's good. 2 times 3 is 6 oxygens. I only have 2, so I need to put a 3 in front. Now that's 6. Now it's balanced. All right. This is, the last one. In fact, I'm 99% sure this is the last one. So decomposition of peroxides. A peroxide is a polyatomic ion we have not really talked about, but it's one we use a lot. Maybe you have this in your house, hydrogen peroxide. So you've heard of it before. Now, who remembers what the prefix per means? Remember when we did polyatomic ions? What does it mean when you do per? Good, it means you add an oxygen. So it's a peroxide. You're adding an oxygen to an oxide, meaning you're adding oxygen to oxygen. So it looks like this, O2. So when you decompose a peroxide, and it's always O2, it's a polyatomic ion, okay? It is not oxygen by itself. It's a polyatomic ion, O2, and it has a -2 charge. Because remember, when we add and lose oxygens, it did not change the charge. Chlorate is ClO3, -1. Chlorite is ClO2, also still -1. Perchlorate is ClO4, it's still -1. So adding and losing oxygens does not change the charge. But when you decompose a peroxide, which is O2, you will always create an elemental oxide plus oxygen. Now notice I didn't say a metal oxide. That's because it's not always a metal. Like hydrogen peroxide. Hydrogen is not a metal. So I use A for any element. So it's going to be AO2. Again, it's always O2 because that is peroxide, yields AO, that's the metal, or not metal, sorry, oops, element, oxide, plus O2, that's oxygen. So be careful. This right here is peroxide. It's a polyatomic ion. This O2 is oxygen. It is a diatomic molecule, hence the O2 there. So be careful. This is specifically why people think decompositions are usually the hardest, or one of the hardest, is because of just this one type right here. So again, in this example, we have, there we go, potassium peroxide, which is K2O2. Reason why is because potassium has a +1 charge. Peroxide's -2. So I need 2 potassiums. And remember, O2, that is the polyatomic ion. It is O2. Yields potassium oxide, K2O, plus oxygen. Another one, magnesium peroxide, makes magnesium oxide plus oxygen. Just to show you a good, hard, kind of crazy looking one, what if it was aluminum? Aluminum. Well, aluminum peroxide. So think, what's the charge of aluminum? It's +3. Good, it's +3. Peroxide is -2. So what do they both go into? They both go into 6. So that'd be Al2. And then, well, I'm going to write it a little bit bigger. Let me write that a little bit bigger. Okay, +3, -2. So again, they both go into 6, so I need 2 aluminums. And then now I got to balance this out. So now I need 3 peroxides. But remember, if it's a polyatomic ion, put parentheses around it. So it looks like that. And then it makes aluminum oxide. ALO, which would be Al2O3 plus O2. And then you can go about trying to figure out how to balance that. If I looked at this real quick, it would take a little bit of manipulation to do, so I'm going to leave that as is. But just to show you again, if you needed more than 1 peroxide, it's a polyatomic, so you have to put parentheses around it. So be careful with that. And that is it. So those are all the different kinds of, again, decomposition reactions. Just to go through them very, very, very quickly, just to kind of refresh. Decomposition, you know it when you see it because it only has one reactant. There's only one reactant. For binary decompositions, you literally just split it in half. Done. When you decompose a carbonate, do you remember? Good. You make a metal oxide plus carbon dioxide. Metal hydroxides. Good. You always make a metal oxide, just like carbonate, just like the metal carbonates. Both of those, a metal carbonate and a metal hydroxide, both create metal oxides, but carbonates make the CO2 and the hydroxides make the water. 2 more. Metal chlorates always make a metal chloride plus oxygen. And then the peroxides always make whatever element oxide plus oxygen. Now you notice at the top it says using MnO2 as a catalyst. I did not write that in there. I need to. So that MnO2 would go at the top, remember. MnO2. MnO2 always goes at the top of the arrow. And that's it. That is decomposition.